So we're going to continue along with this method of using substitution to evaluate indefinite integrals. We've already done one just like this in the last video, so I'll do this one very quickly just to make show the distinction between 4 and 5. So what I might do is I might let your u be 5/8 or 5x plus 9, and that means du is equal to 5 dx. The reason I made that decision is because I know the antiderivative of something to the 8th, or I can figure that out. So I'm just going to replace that 5x plus 9, which is, has all these bells and whistles. I'm going to replace it with just one variable. So now this becomes the integral of u to the 8th, and since du is 5 dx, that must mean that du over 5 is equal to dx. So this becomes du, and there's the 1/5. So this is 1/5, and the antiderivative of u to the 8th is 1/9 u to the 9th plus c. So this is 1/45 u to the 9th plus c, which making our u of 5x plus 9 gives us 1/45 5x plus 9 to the 9th plus c. So notice the difference between that problem and the one in number 5. Number 5 is a definite integral, so we're going to actually get a value here. But we can't do that until we find an antiderivative. We have to apply the fundamental theorem, which means we got to find an antiderivative. So when I see this problem here, what I notice is, that 2x squared minus 7, if you take that derivative, you get 4x. And I don't have a 4x in this problem, but I do have an x. And that 4 is not really an issue. We can take care of that constant and kind of work with it. So I'm going to let my u be the 2x squared minus 7. And that lets my du become 4x dx. And so what you would notice here is if I start doing the substitution here, I'm going to let my u be the 2x squared minus 7, so now that becomes u cubed. What's left to substitute out? Well, I got an x and a dx, right? So what you could do a couple things. We know that an x dx has to be replaced, but look, I have an x dx here as long as I divide both sides by 4. So du over 4 equals x dx, which means I can now just write this as du divided by 4. All right. Now at this point, this problem can be done one of two ways. The first way is what I would recommend, which is, since this is a definite integral, it has a numeric value. These limits of integration up here, 1 and 2, those really mean, even though we don't write it, as x goes from 1 to x equals 2. Now we've just changed this problem to be in terms of u, and that change happened with this relationship between u and x that I've written here. If you're going to continue this this definite integral, your options are to do the indefinite integral like we've been doing, like this one on the left, and then replace all the u's with x's again, and then just go back to the original 1 and 2 here for the limits of integration. But what you could do instead is just change the limits of integration to be in terms of u. So this would be u goes from something to something, and we use the relationship here. When x is a 1, u is 2x squared minus 7, so it would be 2 times 1 squared minus 7, which is negative 5. And when x is a 2, u would be 2 times 2 squared, which is 8, minus 7 is a 1. And so now what you can do is you don't have to go, this is a definite integral, it's going to be a number. We can just pretend that this was the problem all along. The integral 1/4 u cubed from negative 5 to 1. Alright, so no need to go back and substitute for x's. We're getting a number here, so we might as well just we might as well do the easy version here. So the antiderivative of u to the 3 is 1/4 u to the 4th. I'll be evaluating that from -5 to 1. So that's equal to 1/16 times 1 to the 4th minus 1/16 times -5 to the 4th. So that's looks like a 14. That's 1 to the 4th. So that's 1/16, and that's minus 1/16. -5 to the 4th is 25 squared, which is 625. So that's a positive 625. So I could factor out a 1/16. 1/16 times 1 minus 625. So that's 1/16 times -624. And apparently that's a nice whole number. I guess that's -39. Alright, you would get the same answer if you did instead. So that's one way of doing it. The other thing you could have done was you could have said, or I could have just pretended that this definite integral, pretended it's an indefinite integral, which we found to be 1/4 times 1/4 u to the 4th plus the c. But now what we could do is we could turn that back into 1/16. And my u was originally 2x squared minus 7. 2x squared minus 7 to the 3rd. And now the point is to go back to this definite integral. So now what I'm going to do is I'm going to evaluate that from the original 1 to 2. Whoops, it's to the 4th. This is to the 4th. And so then this would become 1/16, 2 times 2 squared minus 7 minus, my use of space is poor right now. Let's move this over here. Minus 1/16 times 2 times 1 squared minus 7 to the 4th. We've got the 4th there. And we get 1/16. So I'll stop it here because you'll see we're going to get the same thing as we got above. This ends up being 8 minus 7 to the 4th, which is 1 to the 4th, so that's just 1. Minus, this is 2 minus 7 is -2 to the 4, -5 to the 4th. So it's 1/16 times -5 to the 4th. You can see that's precisely what we had here, so we're going to get -39 again. So those are your options. I would probably recommend the top way because it's just less substitution. The integrals turns out cleaner. All right. And then the last comment I'll make before you move on is with regard to this problem, because it kind of gets at the heart of why substitution works, or when substitution works. And this is the way I view it personally. I would say substitution, this method, substitution, often works when you see a function and a constant multiple of its derivative within the integral. What do I mean by that? Well, if you look at number 5, The function I'm calling 2x squared minus 7, its derivative is 4x, and what's left inside the integral is that x, or x dx if you include the differential. Notice that x is a constant multiple of 4x. And I mean, I know multiple is a little bit, it's a loose term, but yeah, like I can adjust that 4 to get at x dx, and the substitution will work very cleanly. So just be on the lookout. That's a nice kind of rule of thumb or way of thinking about when would you use substitution.